Justin Miller, Oxford College Physics here. We want to start looking at light. Obviously looking at light, right? You look at light. Yeah, you see things because they're lit up. They reflect light or they emit light. So this is what we want to start studying now is optics, which is ultimately a study of how light interacts with matter and different properties of light and such things. So let us just start off with, what is light? Well, get this out of the way. Light is just electromagnetic radiation. Electromagnetic. Radiation. A lot of people say, radiation, wait, that's bad, right? Like toxic waste. We're not talking about that kind of radiation. We're talking about light, electromagnetic radiation. So ultimately, light consists of an oscillating electric field and an oscillating magnetic field that are occurring simultaneously, that sustain themselves, and that's something that we looked at in the last class, or last semester's class, where we've got induction and all that stuff going on. At any rate, light travels as electromagnetic waves, oscillating. If it's a plane wave, we're kind of going like this. The electric field and the magnetic field, and it travels and propagates through space at some rate. So, light travels through free space. At the speed of light. That makes sense, right? The speed of light, we use lowercase c to denote, and c to three significant figures. We just use 3.00 times 10 to the 8th meters per second. 300 million meters per second. That's pretty darn fast, right? Heck yeah, it is. What is that in miles per hour? Well, roughly double it, and you're in miles per hour. So what are you talking about? 600 million miles per hour? It's actually more than that, right? 2.237 miles per hour per meter per second. So, that's pretty quick. That's really fast. Well, the sun, let's just think about this. The sun's pretty far away, right? It is. It's really far away. About 98 million miles. So light from the sun has to travel 98 million miles to reach us here on Earth. And it's traveling at, say 650 million miles per hour. That's how long it's going to travel in 1 hour though, 650 million miles. It needs to travel 98 million miles. So how long does it take? Approximately, light that is leaving the sun's surface takes approximately 8.5 minutes to reach Earth. What? Yeah, it takes time. It's traveling a really far distance. So think about this. If the sun were to just turn off all of a sudden, somehow it just stopped emitting light, we wouldn't know it for 8.5 minutes, because that's when the last piece of light, if you will, was made. It has to travel that 98 million miles to reach our eyes, and then after that, we don't see any more light coming from it. When you look at the sun in the sky, maybe not directly at it, but when you see where it is, that's not actually where it is in the sky. That's where it was 8.5 minutes ago, because you're seeing the light that's arriving at your eyes that traveled from the sun to your eyes. And this gets all wound up in astronomy and astrophysics. Hey, you're looking at galaxies that are really, really far away. You're looking back in time because you're seeing light that they emitted at some earlier point in time that's just reaching your eyes now. So, in many ways, looking at galaxies and such things gives us an idea of how things were. And then we can look at how things around us are and try to make comparisons about evolution. But that's not exactly what this class is about, right? We're more just concerned with the physics, and that is something that is really important. The speed of light. It's finite. When we're here on Earth, the speed of light is so fast that it seems instantaneous. I flip a light switch on, the light turns on, and for that light to reach my eyes, being that I'm like 10 meters away from it, is time-wise insignificant, not perceivable. Remember, long distances, a couple miles, light seems like it travels through space almost instantaneously, but over long distances, not so much. But there we go, there's the speed of light in free space. Now, free space would mean a vacuum. Now, there's one of the waves that doesn't require a material, a medium, to house it to travel through, light. It's kind of a special type of wave. But ultimately, it can travel through other materials, like it can travel through water, can travel through air, can travel through plastics, can travel through all sorts of different materials, depending on certain properties of the light. And in different materials, it may have different speeds. There are always going to be less than this. But this is through free space. And actually, through air is approximately the same. It's a little bit less than this, but to three significant figures, it's still 300 million meters per second, light traveling through air. Anyways, we've got this going on. So what about light? Well, we've got the light we can kind of categorize into sort of different sections in terms of properties that it has, like radio waves. We have really long wavelengths that are able to go through things and have their own uses, transmitting radio signals. We've got ourselves microwaves. We use some microwaves to cook, and we use them to transmit information as well. What else do we have? We've got ourselves infrared waves. Well, those are generally associated with heat signatures, but hey, it's just a certain type of wave. Light, it's still light. And then we've got visible light, the light that we see with our eyes. We've got infrared light, I don't know if I just said that. Ultraviolet light. Ultraviolet light, you say, oh, ultraviolet light from the sun's bad. Yeah, it can break carbon bonds, has enough energy to do so. And there's blamed for causing cancer and stuff like that. Ultraviolet light exposure to it, not really great. Not great to have too much exposure to ultraviolet light, but it's still light. It's an electromagnetic wave. We've got ourselves all sorts of stuff. X-rays, that's light. It's light, really short wavelengths. Gamma rays, that's light. So ultimately, we characterize light in terms of a category, and ultimately that kind of boils down into what's the frequency of light, or what's the wavelength of light. Usually it's a little bit easier to talk about wavelengths of light because frequencies are very, very large numbers, like 10 to the 14th and such things. So generally we just talk about the wavelength of light, and note that for light waves, the wave relation holds, and that is c is equal to lambda f. C is the speed of light, lambda is the wavelength of light, and f is the frequency associated with that light. So the frequency of the oscillation of the electromagnetic field. So lambda is equal to wavelength, f is equal to frequency. And this ultimately comes from v is equal to lambda f, or wave speed is equal to wavelength divided by period. That's why we say the relation holds. We just use c for the speed of light. And this would be good for a vacuum if it's traveling through something else that has a different wave speed. That's okay. That's what we've got. Well, we're going to focus our attention mainly on visible light. Light that we see with our eyes, because that's what we interact with on a daily basis. If we can do it for those particular frequencies and or wavelengths, we can really do it for anything. But we're going to focus on optically visible light. Optically visible light is a little narrow band within the entire electromagnetic spectrum that has all the different wavelengths and or frequencies of light. Optically visible light has wavelengths that range from approximately 400 nanometers to 700 nanometers. N equals nano, which is equal to 1 times 10 to the negative 9. So there's our N. We talk about visible light generally in nanometers. 400 to 700 nanometers within that band of wavelengths is visible light. Over here, in the 400 nanometer realm, we've got violet, blue, and then, well, we kind of got rid of indigo, but that's okay. Violet end is the 400 nanometer end. As you start increasing a little bit, you get towards the blue, and then you get towards the green. Green, and then what? We got some yellow. I don't got a yellow pin, so I'll just put in the yellow here. And then what? Well, we've got an orange. And then red. So the red end is the 700 nanometer end, and the violet end is the 400 nanometer end. All of the colors of the rainbow are within that band, 400 to 700 nanometers. You may say, well, I heard it was 750 and down to 350. Some of that depends on perceivability. Different people have different sensitivities in their eyes to perceive either shorter wavelengths or higher wavelengths, but this is usually utilized for the violet end to the blue end. You start getting lower than that, then you get into the ultraviolet region. You start getting higher than this, and you're starting to get into the infrared region. So there we go. We've got this little band again of wavelengths of light that constitute visible light. Well, that's a fantastic. What are we going to do with all of this? We're going to start playing around with light and kind of seeing some things. So when you see something that appears to be a different color, like, hey, like this, you say, oh, that's kind of an orangey red color, and I say, yeah, that's what I see too. Hopefully you say orangey red. Anyways, you see this? It's a certain color, right? Why is it this color? What makes it this color? And you say, well, that's the material that the plastic is made of. It makes it that color. And yeah, that's true. That's true, but why do you see it this color? If I turn off all the lights, does it glow red? Reddish orange? And the answer is no, it doesn't. Well, what's going on then? Well, if it's not emitting light, it's not a source of light. It's lit up right now. What's it doing? It's reflecting other light that's in this room, reflecting it, and that reflected light off this is, well, this orangish red color. That's it. It's really due to how the electrons on the surface behave and how they absorb and re-emit light that it's, well, interacting with the surface. But hey, you look at something that's a certain color because of how it reflects light, what colors it reflects, or what colors it doesn't reflect. So we've got that. We've also got what's known as white light. White light has all wavelengths in the visible spectrum. It's a combination. It's a combination of all the wavelengths between 400 and 700 nanometers. And sometimes it may be tinged a color, it may be tinged a little yellow like the sun, or tinged a little green, but if it has all the wavelengths, we can still consider it to be largely white light because you can shine it on anything, and depending on what that is, it will reflect the light that it generally reflects, giving it its color. So that's what we've got going on with light. And white light's going to be important when we start looking at composite light sources and start thinking about what's inside this light source, what sort of wavelengths and why. But there we go, white light, it just has all the wavelengths. So light that doesn't have all the wavelengths are like laser lights. So here's a nice little laser. I'll put this here. I think you can still see it up at the top here. And I can shine it on this, and you get that little green dot there, right? Oh, there it is, just got brighter, great. Green, well, this is green light. That's all it is. It's a certain wavelength, and I don't have my glasses on in here, but I believe it was like 580 or something, 580 nanometers. I forget exactly, I can't read it, but there's a specific wavelength that it produces. And it's nice and collimated, and just puts a little nice bright spot there. Well, I got some other ones. This is one that produces red light, and I think this is around like 632 nanometers, getting towards this 700 cap here. And look there it is, shine it there, and we've got ourselves a different color, because it has a different wavelength associated with it. This one, I'm not sure if you'll be able to see, but this is a violet light. I think this was around like 410, maybe 420 nanometers. And if you can see that right there, we've got a nice violetish color. And up on the board, it looks a little bit more violet because it's reflecting off of something white, reflects everything. Here it's kind of reflecting off of something yellow. Anyways, got those different colors there. And what are they? Oh, it's just monochromatic light, light of one particular wavelength. So that's what we've got going on. Now, you saw that, right? You saw this? I shine it up here. You see that little dot there? Why do you see it? I see it here. What makes you be able to see it? What makes you to be able to see anything is that light from that something is entering your eye, directed into your eye. So when we have a source here like this, and I shine that source here, we get this nice little spot. Let's see, the battery's dying. We've got another green here. We get this nice bright spot right here that's coming from this source, and then, well, that is light right there. That is not, it's not an object. It is the light reflecting off of this surface. But that's the key right there. You can see it, because when it hits this surface, it reflects off and it enters your eye, or at least it's entering the camera so you can see it. I can see it over here. I shine it up there, you should still be able to see it, because when it reflects off of this surface, it actually reflects off in all directions. If I were to shine this light directly into my eye, which I would not do, or directly into the camera, again, which I would not do, it would be much brighter than this. Why is this dimmer than what's actually coming out? Because when it strikes this surface, it reflects off in all directions, so that anybody with a clear view to it can see it. Well, that is a certain type of reflection, and that is known as diffuse reflection. There's also another type of reflection known as specular reflection, and that has more to do with mirrors and such things, things that are very shiny, very reflective, where they can take almost all of the light and reflect it here. So, let me not put that there, because it's going to get in the way right now. I can take this same mirror, and I can take this same laser pointer and take this mirror, and I can reflect it off of the surface here. So I'm shining it down on this, and whoop, I'm reflecting it right back on to that piece of wood there. And look at how bright it is. It's pretty darn bright still, right? It's about just as bright when I just shine it right onto the wood, because I'm not losing much when it reflects off of this surface. Now, probably not going to be able to see this, but you may be able to see a little green stripe across the mirror, and that is because we're getting a little bit of diffuse reflection off of the mirror. But largely, the vast majority of the light is actually reflected wholly off and travels a straight line path after reflection. So again, that's specular reflection, where light travels and just continues on in straight line paths after reflection's taken place. Where diffuse, it reflects off in all directions. So what we want to do is look at those two different types of reflection, identify what is known as the law of reflection, and then reflect on that, if you will, and sort of think about some things. So let us come back momentarily. All right, so we've got ourselves a couple different types of a reflection going on. So let's reflect back on that. Go ahead and write some stuff down regarding it. Ooh, here we go. Got two types. diffuse USC, which is reflection of light off of a rough surface, or I put rough in little quotations there, a rough surface, such that it reflects in all possible directions. And then we've also got ourselves specular. Number 1 there, number 2 there. This is reflection that follows a straight line path. So remains like a ray of light or a beam of light, if you will. So in either case, we've got that there is what is known as the law of reflection. And whether we're talking about diffuse reflection or specular reflection, they both obey the law of reflection. So you may ask, well, what is this law? It seems so applicable to everything. Well, let's get to it. Law of reflection. So let's take ourselves a surface here. And the law of reflection says that you can have some incident ray of light, beam, if you will. So we got some nice culminated light there, or just one particular path of light that we're considering. And it strikes here, strikes this surface, and there's a normal regarding this surface. What happens? Well, it reflects off. How does it reflect off? It reflects off like this. Call that the reflected ray. You may say, well, that seems reasonable. Well, here is what we've got going on with the law of reflection. And this is drawn a little bit suspectly. So let me try to fix this one. Well, it's a little bit better. Because what we need here is this theta sub I is equal to this theta sub R. Theta sub I is equal to theta sub R. That is the law of reflection. That's it right there. We get equal angles of incident and reflected rays relative to the normal, the interface boundary regarding the reflected light. Light reflects off of a boundary at the same angle it was incident upon that boundary. As measured relative to the normal of that boundary. at the location of interface. So here's the interface of the boundary right there. It strikes right there, reflects off at the same angle that it was incident upon relative to that normal. That's it. That's the law of reflection. So you may say, well, didn't you just say that that goes for both diffuse reflection and specular reflection? I said, yes. This would be a nice example of specular reflection. Just got rays, straight line pass, boom, reflects off, straight line path. So what happens when we've got diffuse reflection? Well, diffuse reflection, we're saying that we could have this ray comes in and then it reflects off in all directions. Why? Why? How can it reflect off in all directions and still obey the law of reflection? And we'll come down to the surface. What does the surface look like? Is the surface really smooth like this? Or like a silvered mirror surface? Or does it have some sort of inconsistencies and ridges and bumps and such things in it, like surfaces generally do? Like, even though this this whiteboard seems smooth, it has lots of little inconsistencies in the surface. It's not completely smooth. Most things aren't. And if they're not completely smooth, they have different orientations of the surface normals with respect to different positions. So if we take kind of a zoomed in look at some rough surface, we have that a rough surface may have things like this going on. And then what do? Well, we've got some beam of light. Now instead of just looking at one little path, I kind of say, well, this is a zoomed in view. We've got this beam here. Got this ray of light shining down on this. And what does it do? It strikes the surface. But the surface here doesn't just have one normal orientation everywhere. It has different normals pointing in different directions throughout this expanse over which the light is now overlapping. So what happens? Well, we've got like this portion right here. What's this going to do? Well, it's striking a normal that's like that, and it reflects off that way. That's great. Well, what about this one right here? Well, this one going to reflect off this way, because this is pitched up like that. The normal's like this, equal angles about the normal. And then we've got all this stuff going on in between. It can strike right here and come out that way. It can strike over here and come out that way. It can strike over here and come out that way. And ultimately, what we end up getting is that it's completely diffuse. So we had this whole intensity that was coming down in the ray, and then it gets kind of split up amongst the different directions that it reflects at. And that's why when I was shining this little laser light onto here, it's much, much dimmer than it would actually be if I shined it right into my eye. Because I'm only seeing a small portion of the light, because a small portion of it strikes here and reflects back. Where, well, more of it goes that way and that way and that way and that way, all over the place. So that's what we've got. In either case, we've got the law of reflection is obeyed. Different positions of normals. Or I should say orientations. Orientations of normals at different locations. It really depends on the surface. All right, so that's pretty much that. What we want to be able to do is note that, yeah, diffuse reflection is what's allowing us to see things in general, things that are illuminated with light. Light bounces off them in all directions, allows everybody in the room to see the same things, as long as they have a line of sight to it, and that's pretty nice. That's pretty nice indeed. So what we want to do is mostly look at what's called ray optics. So we're going to look at nice columnated beams of light and sort of analyze them, because diffuse gets hard because it goes in all directions, right? So let us just talk about beams that undergo specular reflection and stay nice narrow beams and kind of move forward from there. So that's what we'll focus our attention on, is ray optics involving specular reflection. So here is a nice little problem just to get some ideas down with specular reflection. What happens if we have two mirrors? Mirror number one, mirror number two. And these two mirrors have some angle between them, which I'll just go ahead and call some angle phi here. And I could have some incident beam of light that comes in. And what does it do? Incident ray. It comes in and it strikes right here, and then it's going to do some other stuff, right? It's going to bounce off of this at equal angles. It's going to hit this one and reflect off of this. And what we could ask is, hey, at what angle does it reflect off of the second mirror, given this scenario? So, how would we go ahead and approach something like this? Well, we need some more information, right? We've got the angular separation between the two mirrors, and then we need the angle of incidence. So we say given angle of incidence is, let's just call that like 75 degrees relative to the normal of mirror number one, and that our angle phi there, we'll say is there's 90, what will add on that? Another 45? Let's call this 135 degrees. The angular separation between these two mirrors. And what do we do with this? Well, we've got ourselves a nice normal there, and we've got ourselves a nice normal there. We've got this angle, theta sub I. I'm going to call it theta 1I. Angle of incidence on mirror number one. And what we want to find is theta 2R. What's the angle of reflection off of mirror number two? How are we going to do this? Geometrically. Most things are going to come down to a bunch of geometry in this, and this isn't that hard. So what do we have? Well, we must have equal angles about this normal right here, right? This here, theta 1R, must be equal to theta 1I. So theta 1R is equal to theta 1I, which is then equal to 75 degrees relative to that normal right there. Fantastic. So then we come on over and we say, well, what about this angle here? We call that theta 2I. This was our angle phi right here. Theta 2I. Well, if we can figure out theta 2I, we know that theta 2R is equal to theta 2I. So theta 2R is equal to theta 2I is equal to what? So how do we get this angle right there? And the answer is, use some geometry. So if I kind of zoom in on this little segment right here, we've got this, we've got this, we've got this beam. It's going like this. Again, zooming in. Got this beam that's going like that. We've got this angle right here, which we've gone ahead and called phi. We know phi is 135 degrees. And what else do we have? We've got this angle is 75 degrees. That's theta 1R. and we want to figure out theta 2i. So one thing that we should note is this and this, the normals make 90 degrees angles with respect to their surfaces, right? That's what normal is defined by. So what we can do with this is we can define a couple other angles. We can define that angle and that angle. Let's call this one alpha, and let's call this one beta. So what do we have to have? Well, we must have alpha plus beta plus phi is equal to, well, how many degrees are in a triangle? 180, that's right. Got ourselves 180 degrees. Fantastic, there's a nice relation between those three angles. One of them that we know. We also have to have that 75 degrees plus alpha is equal to 90 degrees. 75 degrees plus alpha is equal to 90 degrees, which then says that alpha has to be equal to 15 degrees. So now we know two things. We know this and this, which wouldn't allow us to find beta. That's fine, but really we want to figure out what this is. So what else do we have? We've got that theta 2i plus beta is equal to 90 degrees. Theta 2i plus beta is equal to 90 degrees. So we've got all this stuff going for us, and like we just said, now that we know what alpha is, we could go ahead and solve this for beta. So if we solve this out for beta, we've got that beta is equal to 180 degrees minus 135 degrees minus 15 degrees, which is equal then to 30 degrees. That gives us 150, 180 minus 150, 30 degrees. All right, and if that is 30 degrees, this is drawn out pretty good. If this is 30 degrees, this then gives us that theta sub 2i, which is equal to theta 2r, is equal to 90 minus 30. 90 degrees minus 30 degrees, giving us that theta 2r is equal to 60 degrees. That is this angle right there. Not drawn to scale. We had to draw it somehow. I didn't follow nice straight lines, and I kind of guessed at what this angle may be, but that's kind of the gist of things. Look for triangles. That's going to be a really common theme throughout this section, throughout this segment where we're dealing with optics. It's geometric optics. And yeah, there's lots of geometry that we look at. It all turns out to be just triangles. Triangles everywhere. And that's pretty much that. So reflection is pretty easy to deal with. Equal angles about the normal. There we go. All right. Have a good one. More to come. Be well.